thank you all for sticking around for the panel discussion. I'm Hal Evans. I'm a professor in the physics department, and I thought we could start things off by, first of all, me giving you just a quick outline of what it is that we do on Atlas here at IU, and then I'll say a few words about my history and introduce you to the rest of the panelists, and they'll say a couple of words about their work, and then we'll open up the floor for questions. So to start off with, just to expand a little bit on what Rick Van Kooten said at the beginning here, the IU Atlas group started in 1994. Professor Harold Ogren, who's now retired, was the head of the group. We have responsibility on Atlas. We're part of the US Atlas collaboration. The US Atlas collaboration has about 550 authors, people that sign the papers, and about 775 total people working on it. IU played, as Rick said, a very major role in construction of the Atlas detector. We built, as he said, about half of the barrel transition radiation tracker here at Bloomington under the direction of Professor Ogren. We also have major responsibilities for one of the big data processing centers. There are 5 large data processing centers for Atlas in the United States, and one of them is here at IU, shared with the University of Chicago and University of Illinois. Finally, we're now starting to build some high-speed electronics for upgrades to the Atlas detector. And then we also, of course, being physicists, also do analysis of the data that's collected at Atlas. And we've looked for all kinds of different things, various types of exotic Higgs bosons, supersymmetry. We are studying the properties of the B quark and the hadrons that it creates. And we're also looking at the details of the Higgs mechanism, some of the mathematical details of it. So those are the kinds of physics that we do. Our group is a medium-sized group for university groups on Atlas. We have 12 physicists involved, 3 faculty, myself, Professor Van Kooten, and Professor Sabine Lammers. Professor Ogren is retired now. We have 2 research scientists, one of whom is Daria Zieminska, sitting here on my left, and also Fred Luring. We've also had a research scientist that's recently retired, Pauline Gagnon. We have 2 postdocs, Nare Lorenzo and Cimo Poveda. Cimo just recently got a CERN position and has started that a couple months ago. And we currently have 5 graduate students working with the group, Kyung-An Choi, Aparajita Dattagupta, Alex Johnson, John Penwell, and Ben Weinert, who's also sitting here on my left. And then we use the services of a few engineers part-time. We're working with 3 engineers and technicians right now, Paul Smith, Brandon Kunkler, and Brian Martin. And finally, we have an administrator that looks after us all, Jenny Stevens, part-time. So our group it's a great group. It's a lot of fun to work with, very nice people, and it's really been very productive. I'll tell you just a few words about my history in physics. I have a long history with CERN. I went to CERN as a graduate student first in the summer of 1988 with the intention of staying there for a year and a half to collect data for my thesis. Nearly 10 years later, I finally made it back to the United States. I spent a long time at CERN. I was a graduate student there with UCLA working on the UA1 experiment, which discovered the W and the Z boson. That's part of the particles that you saw today. I was also a postdoc for the University of Chicago on the precursor to the LHC, the Large Electron Positron Collider, LEP. In fact, I worked for University of Chicago, and my boss was the same as the boss of Monica Dunford, so there's a nice little synergy there. In 1997, the end of 1997, I moved back to the States and took a faculty position at Columbia University. There I concentrated mainly on work at the D0 experiment, which is an experiment on another big collider, Fermilab, just outside of Chicago that some of you may have heard of. And finally, in 2005, I came to IU and joined the faculty here and have been here ever since. My research involves a few different lines. I look for new physics, physics beyond the standard model, as it manifests itself by making modifications to things that we've already seen, studying things like the B quark or the tau lepton. I also am involved in designing and building very high-speed electronics that allow us to select interesting data out of the huge pile of data that the LHC delivers to us. And finally, I've become, as time goes on, more and more of a manager. My current position at Atlas is I'm the technical coordinator for the US part of the long-term Atlas upgrades, which will be installed in 2023. Very interesting role. It allows me to participate in all the different technologies that are required to meet the challenges of the increasing intensity of the machine and the increasing power that it's running at. So it's a very, very exciting time. So I'd like to now introduce you to the rest of our panel, and they'll say a few words. We'll start off with Denver Whittington, who was a graduate student with me and is now moved on to neutrino physics. Go ahead, Denver.
Thanks, Al. Yeah, I was a graduate student here at the IU Atlas group, and starting in 2006, I guess. I spent 2 years at CERN working on software for controls and monitoring of the transition radiation tracker. Just one of those tasks that requires a lot of effort. There's a lot of people working on these projects, really sophisticated electronics. A really fascinating project to really work on. I came back in 2009 to Indiana to focus on physics, where I was working on top quark physics analyses with Atlas. I transitioned to working on top quark physics analysis on D0 that Hal mentioned. This is another similar detector to Atlas, based at the Fermilab Tevatron Collider, which has just recently been decommissioned a couple of years ago. Worked on top quark physics analysis on that, and then graduated with my PhD in 2012, just a few days after the big Higgs celebration, Higgs Pendants Day we called it. And that was a real blast to see, and I even got to cite the paper in my dissertation. And then I afterwards transitioned to the next area of sort of big question mark in the standard model of particle physics, which is the neutrino sector. These ghostly particles exhibit a lot of features that really aren't well explained by the standard model so far. So it's another big puzzle that I'm really excited to continue working on with colleagues at Fermilab still, and colleagues in another group here at Indiana University.
Hi, so I'm a graduate student here in my 4th year, and I work on Atlas. And I do something very different than what you saw in the movie about Susie and the Higgs, which is possible because, unlike some of the other detectors, Atlas is a general purpose detector. So it lets us basically study whatever we could think of and try and find new things. My research mainly focuses on double parton scattering, which when you saw in the movie, the accelerator basically shoots 2 protons at each other. And usually what happens is when those protons collide, one of the quarks or the gluons, which holds the quarks together inside the proton, they provide an event and you study that. But at the high energies that you reach at the LHC, it's possible that you can have multiple collisions of quarks inside the protons and get double parton scattering or multiple parton scattering. And because that's produced at a non-negligible rate, that's quite interesting. It could be a background to a lot of Higgs or Susie effects. The reason why I'm mostly interested in it is because you can learn a lot about the inner workings of the proton and hadrons. There's a lot to be learned about that. And it's interesting because it's a completely different area than anything you've seen here. And basically you can just see that Atlas has a ton of things going on. It's not just Higgs, it's B physics, flavor physics, anything you could think of. Besides that, as a graduate student, if you might have seen a lot of them in the backgrounds of that movie, they give us all service projects that we have to work on. So mine is focusing on the transition radiation tracker, which we built here, which basically is a detector made up of straws filled with gas, and they have a metal gold wire in them. And when an electron passes through it, it knocks out more electrons in the gas, and you get a signal. But due to the high radiation you can get at the LHC, more so than anywhere else really, you can have issues like aging or buildup on the wires that could decrease your signal. So my service project is to basically build a monitoring system to see if this is something we need to deal with, or if it's becoming an issue to decrease in signal. So I guess the one really interesting thing is all the responsibilities they give the students. And so those two things are basically what I spend most of my time on.
Thank you, Ben. Daria?
My name is Daria Zieminska, and as my colleagues mentioned before LHC, the biggest collider was at Fermilab near Chicago, and there were two experiments, D0 and CDF, and the collider is now defunct, but there are still 900 physicists who are working on the data. There are still a lot of questions to answer, and the Fermilab data are unique, different from the LHC data, because it was proton-antiproton rather than proton-proton in collisions. So I'm one of those 900 physicists working on Fermilab, and about 1/3 of them are also working at Atlas or CMS at LHC. So I also work on Atlas, and I advise Ben on his physics analysis, this double parton scattering. Now, I think in this company I'm uniquely qualified to tell you how CERN and particle physics world has been changing over decades. So I spent a couple of years at CERN in the 70s, and at that time it was a small club of Western European countries. And as you know, CERN is an acronym, and E stands for Europe, but as the CERN director said recently, that it's more appropriate to say that E stands for everyone. And to give you an example, Ben has to report on his work at regular meetings, which we join via video conferencing. And so he reminds me, on Wednesday there is a meeting, and remember, I want you to be there because there will be important decisions and questions, but it's at noon at CERN. It means 6 in the morning for us. And I was a little annoyed because they could accommodate us a little better until I realized that a group from Sydney is also joining. So that there were a few, there was a Greek group, a few groups from England, CERN of course, and us, and this is how we work. So I wanted to share it with you.
Thank you, everyone. So, please, feel free to ask questions. There's one there.
Please give us an update on the current status of research at CERN. Apparently, the collider has not reached its full capacity anticipated, and did the film, which ended about two and a half years ago, did it mention that it was being closed down for a period before continued research?
Yes, so maybe I can take this one. Yes, so we've been in a shutdown now for almost 2 years. The shutdown started in early 2013. The primary purpose was to complete the modifications that are needed to the magnets to allow them to run at their full energy. And we're here actually at a very good time. We could be better, but it is a very good time. In probably 2 days, beam will start circulating again in the machine at about twice the energy that it was at previously. This is still slightly below the design energy. The reason is it will be running at 13 TeV rather than 14 TeV. The reason for that is that the machine people, having learned their lesson of pushing things too hard, are going slowly. So the plan is for this year to run at this slightly reduced energy, 13 TeV, as opposed to 7 or 8 TeV. And then next year, we'll see, and maybe we'll go up to 14 at that point. But this is still a huge step in energy, and so when we start seeing collisions, there's a real hope that we'll start seeing new particles that were too heavy to be produced at the previous energies. So it's a very, very exciting time right now. Yes?
You mentioned double. Is it double the beam energy or double the if you double both of the beams, then you've got obviously more than double the power going to the collision.
So the question is this double the beam energy, or is it double or is it something else? And the answer is it is something else. It's double the center of mass energy. So center of mass energy gives you how much energy is produced in the collision that can be transferred into making new particles. So our last run was at 8 TeV. This next one will be at 13. Hopefully we'll move up to 14.
But also the beams will be better focused and colliding more frequently, so there will be much more data.
Please.
So finding the Higgs boson was obviously the central point of the film that we just saw, but it's also been a central selling point of the initial run. With the increased energy, is there a particular goal in mind that people have as far as what will be discovered, or is it really a sort of grab bag where you don't know what will be coming out when you run it at close to full speed?
So the question is, do we know what we're going to find? To paraphrase you a little bit at the new energies, and I think this is something that I'll let everybody have a word on.
We hope for supersymmetry. Yeah. We hope for finding all those missing particles. You heard that every particle that we know has a super particle partner at a much higher mass. We haven't seen them because even at Fermilab there was not enough energy. They were searched for, but they were not found. And we really hope that they will be found.
And then there's also the precision studies of the properties of the Higgs itself. We can measure how often does it produce two B quarks versus how often does it produce two W bosons. We can ask these questions about the detailed properties of the Higgs boson and hope to learn more about it. And those are also some other avenues for potential new physics to sort of squeeze into the picture as well.
Basically, if you go to any conference now, a lot of places, if I've been in a lot of B physics talks, and a lot of people have rare B mesons that they want to see, but they can only set low mass limits. So I guess, yeah, and producing any type of high mass particle, they have ideas of what they want to see, but pretty much getting anything higher mass is what we're hoping for.
So the basic problem is that our theoretical friends have had 40 or 50 years to let their imaginations run wild, and they really have done that. And there are a lot of good ideas out there. We don't know which ones are true yet. There was very true that what we've seen now raises more questions than it answers. We don't know what's out there. That's part of the joy of it. Yes, please.
Can you say something about the data acquisition, which apparently the Higgs cross-section is small, so you don't create very many particles, and you get a huge number of events that you have to sort through. And if you're just interested in the Higgs, you throw away a lot of stuff. But it sounds like there's useful physics in some of the stuff that you can look at besides searching for the Higgs. So it's not just the accelerator physics or the detector or accelerator technology or detector technology. It's also the data acquisition and data analysis.
Exactly. So the question is, could we explain a little bit about the data analysis, the data acquisition techniques that we use? And indeed, this is a very important
Triggering.
thing. Yeah. So this is an area that we are right now getting involved in at IU. If you look at the rate of interactions, so I'll throw out a few numbers and then I'll let everybody else give their impressions as well. If you look at the rate of data that we're taking, we see almost 1 billion proton-proton collisions per second. If we took all of that data, it would fill up 100,000 CDs with data every second. So clearly, that's not something that the US government will give us money to do. So we have to only select those events that are particularly interesting. It turns out that the events that we're interested in are very rare. As you say, the Higgs boson occurs about once in every 10 billion proton-proton interactions. It's very rare. So we need to design electronics that's fast enough to understand, to be able to decide whether this is a collision that might be interesting or if it's something that we've seen many, many times before and don't care about. That's called a trigger system. The difficulty there is that these things are happening, these collisions are happening every 25 nanoseconds. So you have 25 nanoseconds to figure it out. This kind of stuff is very, very, it was, in fact, still does to some extent, drive a lot of the telecommunications industry. A lot of the high-speed electronics that you see, for example, in your cell phones came out of things that happened in high-energy physics a decade or so ago, driven by these very high data rates. This is the original big data. So maybe you guys can chime in a little bit on how you've been involved in analysis and this kind of thing.
Yeah. Well, I guess one of the things I have for my data is it's quite a rare event. It's these two J-psi particles getting produced. And it's a multi-layer trigger system where you have a level 1, a level 2, and then an event filter. And for the event filter, if you can pick out certain physics events. For instance, I want something with 2 muons with a minimum momentum of 4 GeV. There's a trigger for that because at the event level trigger, everything gets sorted. And there's, at least I've worked a little bit with the B-physics trigger group. And for every physics interest, there's people who work on triggers for those as well.
I like to do physics analysis. We are all experimentalists. You heard theorists and experimentalists and the joys of each. So, as Dimopoulos said, he builds a theory and then he has to wait for experimentalists to tell him the truth. The data will show the truth. And what is exhilarating for us, experimentalists, that we are attracted by some theory, we want to test it. I write a computer model, a computer program that accesses the data, organizes the data in an optimal way for this particular question, and then run the program, and I am the first to know the truth. So this is really a great joy.
There was another question over here. Steve.
Approximately how many Higgs bosons will be seen in the Atlas detector in the next run?
Okay.
Oh boy. Does anybody remember the Higgs cross-section? So we expect in the next run, if you call the next run the next 3 years, which is run 2, we will collect about 150 inverse femtobarns of data. That's a measure of how many collisions there are in physicists speak. The cross-section for the Higgs is what, a few picobarns. It's tens of thousands. Yeah.
You said 1 every 10 seconds, about what would that be
Sorry, could you repeat the question?
1 Higgs every 10 seconds. Was that for an ATEV or is that for
Sorry, I'm always forgetting to answer to repeat the question. His question was 1 Higgs every 10 seconds. Is that at 8 TeV or at 14 TeV? It's at 8 TeV. It's actually more like 1 Higgs every few minutes, I believe, maybe 30 minutes. I don't remember exactly off the top of my head. The probability of production of the Higgs goes up with higher energy, but it doesn't go up that much. So it's not a huge effect. The big thing in going up with energy is that you can produce more massive particles. And so if there's new stuff out there that's heavier, which many theories predict, when you go up in energy, you can see it then. Yes, please.
The poster with the very strange particles on it, is that a one of a kind, or is it actually printed?
It is printed. Yeah. Sorry, the question was about the poster that you saw in the film. It's a poster by Roz Chast. That was the cover of Symmetry magazine. So if you Google Symmetry magazine Roz Chast, you can download a copy of that for your very own. I personally have one hanging in my office. Yes.
Earlier, there was a mention made that after Fermi Lab's been shut down for a number of years, there's still 900 physicists studying the data. How much data in comparison is going on at the LHC?
So the question was, how much data is there at Fermilab compared to the LHC? Maybe.
I'm not good at such numbers, but orders of magnitude more. But as I mentioned, Fermilab was smashing protons and antiprotons. So it can answer questions that LHC cannot, because it's different collisions.
And ones that are really important for the Higgs analysis too, right? Like the W mass, for example,
Yes.
has it probably won't be measured better than Tevatron's measurement for a very, very long time. I don't think the LHC is really in a good position to do that measurement as well. Yeah, so there's a lot of valuable data from the Tevatron data set. And there's other projects going on at Tevatron too.
Yes. There is still a lot of momentum.
There's the 900 physicists on D0 still. There is
D0 and CDF.
and CDF. There's a strong representation from the CMS detector, the other sort of complementary detector to the Atlas detector. The U.S. Sort of stateside control room, remote control room for CMS is there at Fermilab. And then Fermilab is transitioning to a very strong neutrino physics platform and generating nice, very, very powerful neutrino beams there.
Yes, please.
As the energy goes up on the collisions, how stable are the masses of the other particles? Are people sort of checking in and hopefully seeing the same kind of mass independent of the energy for the known particles?
So the question is, how stable are the masses of the known particles as you go up in energy, as we start a new runs? The answer here is that every time we start over again, we rediscover all the things that we found before. So if you remember Monica Dunford talking about rediscovering the standard model when the LHC turned on, that was checking that all the particles that we know about are still there and have the right masses. Right? If they didn't, then there would be something wrong with the detector.
Masses of particles don't depend on the energy of the collisions. They are properties of those particles, but the calibration of the detector is another matter. They'd better be the same. So,
in fact, a lot of the analyses depend on that. We have, like, for example, the Z boson has been so well measured before that it is a very useful calibration for the LHC. We can look at the particles coming from that and the mass that is measured by the Atlas detector for that particle and make sure that everything is working correctly.
Yes.
Do you have an estimate of how long this about to start run will have to go before you see something interesting, or do you have to estimate the cross-sections of the unknown particles first?
So the question is, do we have an estimate of how long it might be before we see something interesting? The short answer is no.
but you saw the movie. if the Higgs was at 115, it would be much sooner than 125, I think.
I always felt like there was kind of a cottage industry for producing expectations for before the actual startup, where you took your favorite theory, your particle that you would predict, and a cross section for that particle versus its mass, and so you could say, okay, well, if it's 500 GeV, here's the cross section, here's the number of events we need to collect. If it's 800 GeV, we need to collect more events before we see it, and so you can kind of push it on up higher and higher, kind of with a lot of the supersymmetry particles.
Yeah, well, one thing to keep in mind here is that in the film they pushed very strongly two different theories, supersymmetry and multiverses. That's by no means representative of the vast array of theoretical ideas that are out there. And so you
Also,
shouldn't come away with the impression that that's all that we're looking for.
Also, they are not mutually exclusive.
Right.
They wanted to build excitement, but they simplified the situation.
Yes.
You sort of just answered my question, but I also have want to just tell people there's another wonderful movie about Fermilab, which is,
Yes.
I believe is called Atom Smasher.
It's called The Big Bang Machine, is that it?
Film 137.
I just saw it and I've forgotten what it's called.
Yeah, that sounds
It's Adam
familiar.
Smasher's? Okay.
That sounds familiar.
By the way, there is a very, very new film that I have a copy of the poster. The title is Symmetry. It's a dance and opera inside the CERN LHC. So it was written and directed by Ruben van Leer, a Dutch person. So watch for it. There is a website. This is www.symmetrymovie.com. If you like this film and Interstellar, you may like this.
Yes, please.
So for the television program, The Big Bang Theory, has this had a positive influence on your field, a negative influence on your field, or has it been a mixed bag?
So the question is The Big Bang Theory. I think our younger colleagues will have to answer
Mixed
that.
bag. It's nice to have people care more about physics, but I guess it depends on who you ask. There are a lot of people who are getting tired of asked if they're a Sheldon in the group.
Mm-hmm.
So it's great for publicity sometimes, but
I know a lot of us, myself included, that kind of find the characters portrayed in the show almost as kind of off-putting as like the typical dumb blonde, and kind of this ultra, exaggerated caricature. But at the same time, it's I think the show is representative of this shift towards embracing quote-unquote nerd culture, or really popularization of science and appreciation for that. And I think that to me is it kind of overtakes and places this trend in sort of the good category overall.
Everywhere except Congress.
Everywhere except Congress?
Yes.
So if there's a sequel to this movie, is it going to be called Sparticle Fever?
Nice.
We can only hope. Yes.
Just as an aside, at the very end, they showed the Cave of Forgotten Dreams. As you may know, Lascaux is basically a dead cave at this point, pretty well destroyed. Almost the moment that cave, the Cave of Forgotten Dreams was discovered, they closed it. And there's very limited research allowed, but they have just constructed a replica very close to it that is now open to the public, or will be in a week or two.
Nice.
Just FYI.
So again, the comment here was that the Lascaux caves, although
The cave.
was it
It's
Lascaux?
not Lascaux.
Chauvet. Yeah. Sorry. Yeah.
Of the Forgotten Dreams.
Yeah. Right. Is the replica is open to the public?
Yeah.
Yes. Question in the back.
You mentioned the speeds starting at 8 and 13 this year and going to 14. Is there a high-end goal for the speed that we're going to keep going up and up and up?
So the question is, can we keep going up and up in energy? And the answer is that 14 TeV is pretty much it. They could conceivably push a little beyond an energy of 14 TeV, but it would stress the magnets very heavily. There's discussion of going to a high energy machine, but that's a very, very big thing. You either need to replace all of the magnets in the machine, or you need to build a new machine, dig a new tunnel. Those discussions are ongoing, but that's very far in the future, even on a high energy physicist's time scale. Well, in fact, underneath the Lake Geneva is the idea. Kind of underneath Lake Geneva and then back under the mountains, under the Jura Mountains, would be a huge machine.
Does that include a possibility of Texas being revived, or would that be done?
So the question was, can Texas be revived? No, it cannot. The Congress mandated it that the tunnel be filled in. That was not a pleasant time. Yes, please. Wait, sorry. Maybe
sorry.
he's been waiting patiently. You're not.
Well, I was just curious, the CERN cyclotron or whatever is divided into 4 or 5 different control rooms, is that right? Alice, the LEC, what does each respective unit do? Can you briefly describe what those do?
Certainly. So the question is, what do the 4 experiments that are on the LHC do? Do we each want to take one?
Sure.
I'll take Atlas. You know what it does. Go ahead, Dan.
Okay, let's see. If I go clockwise around the ring from Atlas, Atlas is closest to CERN. It's at one of the 8 interaction points, places where the 2 beams could cross each other if they wanted to. It's closest to CERN. Next around clockwise from top is Alice, in French pronunciation. It is you saw Atlas is sort of symmetric. It's barrel-shaped and has basically a symmetry along the beam axis. Alice is designed to look at, specifically like Ben was mentioning, in fact, I should have left this for Ben, B-physics studies.
That's LHCb.
Oh, this is LHCb. I'm going the other direction. If I go counterclockwise, go clockwise around the beam, towards Alice. Alice is another similar cylindrically symmetric detector instrumented with a very high granularity to study heavy ion collisions. And it's the other mode that the LHC can operate in that we didn't actually see talked about here, but instead of colliding protons with protons, they can actually drive heavy ions like lead ions and gold ions into each other, either into protons or into each other, and study a whole different category of nuclear physics called heavy ion physics. And I'll stop there because I don't want to ramble about that. But it's a very different experiment, and it's very interesting in its own right.
So I think continuing in the same path, I forgot if we're going counterclockwise or clockwise, but I think the next one is CMS on that route, which is just like Atlas. It's a general purpose detector, unlike ALICE or LHCb. So basically, it's going to look at whatever it can find. It stands for compact muon solenoid. So unlike Atlas, it's a lot smaller, and I think it's about half the size.
But like twice the weight or something?
Yeah, it's very compact. So like Atlas, that's another general purpose detector looking for whatever it can find.
You want to do LHCb?
LHCb? LHCb is different from all the others because it's not a cylinder around the beams, but it is a one arm, so it's has only one part. But it's so a very good instrumentation of particles going in one direction. And it is optimized for particles that contain a bottom quark. So that's why it's called LHCb, B for the bottom quark. And there are lots of questions about particles containing the bottom quark. which not only about those particles, but they carry information very important for us, such as why there is a preponderance of matter over antimatter. And for the matter to be more abundant than antimatter, there must have been an asymmetry, a breaking of a perfect symmetry. The buzzword is CP symmetry. C stands for reversing the charges of all particles in an event, and P parity is looking at an event in the mirror. And when those two operations are performed, if everything is symmetric, such two events should be exactly equally probable. But for us to exist, for the matter to, and antimatter not to annihilate completely, and there would be only light, but nothing else, there has to be a CP violation. And LHCb is looking for those, for a tiny difference between probability of an event to be more probable than this mirror image. So looking for CP violation if you want to Google it.
Yes, please.
In the group photo, the guy joked about the spare detector. Is that just a painting on the wall?
Yeah.
So the question was the spare CMS detector. That actually is a hanging that hangs in the big office building where a lot of the Atlas and CMS people are. So it's several stories tall. It's almost full scale. Yes, please. Oh. So I think we're getting close to needing to wrap things up. Maybe one more question, if there's anything else that anyone wants to ask. Yes, please.
Can you say something about the stuff that was actually fabricated at IU? Was it just read electronics, or was it plastic cylinders, or wire chambers, or what part of it was actually fabricated?
So the question was, what was actually fabricated here at IU? So it was actually a detector components themselves. The transition radiation tracker has three main components. It's got a kind of drinking straw, essentially. They're about 1 meter long. They're made out of various materials. Carbon fiber is one of them, but wrapped with other things. In the center of that is a gold wire that's platinum-coated gold wire that runs through the center of each of those straws. There are about, in the barrel detector, there are about 50,000 of those straws. And yeah, and those straws then are embedded in a kind of a polystyrene foam that's useful in producing this transition radiation that the thing is supposed to detect. And so here at IU, we did all of that. We didn't make the straws. We got the straws, but we strung the wires. We put them together into the modules. We built the modules, which is a collection of straws in there and these foam radiators. And I shouldn't say we, I was not there at the time. This was Professor Ogren, but I feel like it was me because I've been working on the TRT for so long. But yeah, we put the whole thing together and shipped these modules off to CERN, where they were then constructed into the full barrel TRT and lowered into the pit.
So these gas filled?
They're filled with a mixture of, well, Ben, you can.
So originally they were going to be filled with a mixture of, if I'm not mistaken, xenon, carbon dioxide, and CF4. I forget what the name of CF4 is. But then there were some issues, I guess, with if there's a certain level of moisture or water in the air, CF4 can form acid, which obviously could not be good for our detector. So currently, I think it's a mixture of xenon, CO2, and oxygen. But there's talks of switching to argon or cheaper gases than xenon.
So that's right. It's about 70% xenon, 20% CO2, and 2% oxygen.
Well, CF4 would be carbon tetrafluoride, right?
That's right.
And that's poisonous.
A lot of stuff is poisonous. The problem with CF4 is that it attacked. There's various glass pieces, and it attacked the glass and ate it, which caused, needless to say, some grief for the detector. So, unless there is anything else, I think we would all thank you very much for coming, giving us a chance to share our passion and our joy at this wonderful detector and to watch this great film about it. Thank you very much, and we'd be happy to answer any other questions for you if you come up afterwards.